Hello and welcome to the Further Maths Support Programme revision recordings for A-Level modules. In this section we're going to be looking at MEI Mechanics 2 and specifically the momentum and impulse topic. Here are the basics that you need to be clear on from the specification. You need to think about momentum and impulse being treated as vectors and be able to calculate the impulse of a force as a vector. You need to understand the concept of momentum and appreciate that it's a vector quantity, and you need to be able to understand and apply the impulse-momentum relationship in a number of different problems. Secondly, conservation of linear momentum. Understand that a system with no external forces acting on it conserves its momentum. Be able to derive the conservation of momentum equation for a collision between two particles in one dimension. Be able to apply the principle of conservation of momentum to direct impacts within a system. You need to have the idea of coefficient of restitution from Newton's experimental law to be able to use this in modelling impacts. You need to be able to solve problems using both conservation of linear momentum and Newton's experimental law together. And you need to understand that unless the coefficient of restitution is equal to 1, mechanical energy is not conserved, and to be able to calculate how much energy is lost in an impact. You need to have the techniques for oblique impact with a smooth plane. So impulse acting in a direction that's normal to the plane, to know that the velocity of the object parallel to the plane is unchanged by the impact, to know that the direction of the component of the velocity perpendicular to the plane is reversed and that the magnitude of that is multiplied by the coefficient of restitution, to be able to calculate loss of kinetic energy in an oblique impact and be able to solve problems surrounding this particular topic. So we're going to start with an exam question here. If you're working on these questions at home and would like to go through the question yourself before looking at the solution, bear in mind that I've shown the initial setup for the question on this slide. The questions themselves are on the following slide, and then when I move to a third slide after that, I'll be beginning the solution. So you may want to pause on this slide and work through the questions yourself before I move ahead, as I'm about to do now. Okay, so we have these two sledges. They're connected by a horizontal rope through the middle. One has mass 200 kilograms, the other has mass 250 kilograms, and in the initial situation they're both moving forwards with a velocity of 5 I meters per second. And notice that the velocity here is given in vector format. Please excuse me. In vector format. So a mechanism on Q jerks the rope so that there's an impulse of 250 I newton seconds on P. So we need to consider P only in this initial situation. Because we're given an impulse, we don't want to look at the system as a whole, at least initially, because that would remove the impulse, because there'll be an equal and opposite impulse acting on Q, which would cancel out the one acting on P. So first of all, we want to look at impulse equals change in momentum. But we're going to look at P only. Now remembering that impulse and momentum are vector quantities, impulse, excuse me, we're given as 250 I in this case. Change in momentum then, we're going to do final momentum minus initial momentum. So final momentum is going to be 200, that's the mass of P, multiplied by the final velocity of P. That's the value we're looking for. And we're going to subtract from that the initial momentum for P, which is 200 times 5I, the initial velocity. If we rearrange that, we end up finding that UP is indeed equal to 6.25 I, as requested in the question. We can then do the same type of calculation for Q, but being careful with directions here. P is excuse me, pulled forward by an impulse acting in the positive I direction. The impulse acting on Q will act in the negative I direction. So the impulse on Q is given by minus 250 I. That's going to be equal to final momentum for Q, which is going to be 250, I'm going to call that final velocity UQ, minus 250 times 5I. The initial momentum, rearranging this, gives me UQ is equal to 4I meters per second. So the new velocity of Q after that impulse is applied, 4I meters per second. Okay, marks for this one. There's a method mark for applying impulses changing momentum. There's an E mark for showing the result that was required here. A method mark for using impulse equals change in momentum for Q, and an answer mark for the 4I meters per second. Going on then to the next part of the question. So there's now a direct collision between the sledges, and after the impact P has this new velocity. I'm just changing the velocities here to the ones that we had in the previous question. So P is moving with 6.25I meters per second velocity, so it's catching up with Q, which is going at 4 meters per second. Sorry, my mistake, 4I meters per second. So you can see, as I say, that P is catching up with Q because it's going that little bit faster. So we would expect there to be a collision between the two, and we're told after the impact P has this velocity 4.5I meters per second. So this time now we're not interested in the impulse acting on either of the two objects, so we need to look at the momentum for the whole system. So we're going to use principle of conservation of linear momentum for the whole system altogether. Initial momentum then for P is mass times velocity. Initial momentum for Q, again mass multiplying velocity. After the impact, we've got momentum for P is going to be 200 times this given 4.5I, and we're going to add to that the new momentum for Q, which we're going to call 250 VQ. Okay, so most of this now is numerical. We can rearrange it, and we end up with a value for VQ of 5.4I meters per second as required. We then have to find the coefficient of restitution in the collision. Well, it's a bit of a dead giveaway if we're looking for coefficient of restitution, that we're going to have to use Newton's experimental law. That states that coefficient of restitution is equal to separation speed over approach speed. Now, both sledges are going in the same direction as each other, both before and after the impact. So our separation speed, if VQ is going at 5.4 meters per second, and P is also moving, P is moving towards Q at 4.5, then their separation speed is going to be 5.4 minus 4.5. The 5.4 is moving away from P, so it's contributing to the separation speed. The 4.5 is towards Q, so it's reducing the separation speed, so it becomes a negative when calculating the separation speed. And similarly, before the impact, P is moving towards Q with a contributory speed of 6.25, but Q is moving away from P, so we reduce the approach speed by 4 to compensate for that. This gives us a value of 0.4 for E, which is our answer that we're looking for. Notice that that is a value between 0 and 1, which is as we'd expect for the coefficient of restitution. Marks for this one, method mark for using conservation of linear momentum here, an F mark for doing this correctly, and an E mark for giving the required value of VQ. In the second part of the question here, a method mark for using Newton's experimental law, an answer mark for correct signs in this part of the calculation, and an A mark, answer mark for the 0.4 at the end there, correct answer only. Okay, moving on to the third part of the question. So the rope becomes taut again. I'm just going to put in the speeds that we got out of that previous part of the question. So now P is moving at 4.5I meters per second, and Q is moving at 5.4I meters per second. And in actual fact, in this part of the question, we're not interested in what's happening with Q, we're just interested in what's happening to P. So before, I'm just going to do a quick before and after sketch here. Before the impact, P, excuse my badly drawn diagram here, P, which has mass 200, is moving forwards at 4.5 I. After the impact, the sledge is still moving forwards, and it's the final velocity of that sled that we're going to be looking for. Oh, sorry, no, my mistake. You're told that the new velocity of the sled is 5.5 I. We also have this part which is thrown backwards, and it's thrown backwards at some multiple of I. So its velocity here is, I'm going to call it minus Ki, and this has mass 20 kilograms, which means that the remaining mass of the sledge at P is going to be 180. There's no external impulse being applied in this part of the system, so we have, again, principle of conservation of linear momentum is going to apply here. So before the impact, 200 times 4.5 I. After the impact, 180 times 5.5 I minus 20 Ki. For some value of K, if we work that through, we can find that K is 4.5. So that means that the package, or the part of the load that's thrown out, the 20 kilogram chunk that's thrown out, goes out at minus 4.5 I. That means that their separation speed is going to be a total of 5.5 plus 4.5, which gives us a separation speed of 10 meters per second. Okay, marks for that one. Method mark for using principle of conservation of linear momentum, a B mark for the correct masses, and an A mark for finding K is 4.5, and then separation speed, A1 for putting the 4.5 into here, and F1 for ending up with the result of 10. Moving on from there. So the sledges now collide again. Again, let's get our speeds into this part of the diagram. So P is now moving forwards with 5.5 I velocity, having had its bit thrown out. Q is moving with 5.4 I meters per second, so P is just moving fast enough to be able to catch up with Q. This time they bump and they then stick together. Notice that the sledge P now is 180 kilos. So again, I'm going to do a quick before and after. This is P and Q. This is 180, and this one 250, with velocities 5.5 I and 5.4 I. The two coalesce together. After the impact, then we've got a total mass of 430. That's P plus Q stuck together, and I'm going to say that they're moving forward with a velocity v here. Linear momentum is conserved because no external impulse is applied in here. So again, just using principle of conservation of linear momentum, we have mass times velocity for P plus mass times velocity for Q equals total mass times final velocity for the combined system, and rearranging this gives us V equals 5.44 I, and that's rounded to 3SF as requested in the question. Okay, so marks for that one, just 2 marks. So a method mark, principle of principle of conservation of linear momentum, and a single answer mark, correct answer only. Okay, so that covers that first large question. I'm just going to go through a couple of excerpts from a question here from June 2011, question 1. Just picking out a couple of extra little topics here that may be of use. So again, if you're watching at home and would like to work this through yourself, do please pause at this point and make that calculation because I'm going to start on the solution. So we have these two spheres and initially P has a velocity of minus 1.75 metres per second, and it's acted on by a force of magnitude 13 newtons acting in the direction PQ. So initially P is moving in that direction, and we have this force of 13 newtons acting on it. Again, we're going to use the idea of impulse equaling change in momentum. We're just looking at P only here. So impulse equals change in momentum for P, because that's the only part of the system that has an impulse acting on it. And just to note that impulse is force times time. So we have 13 newtons being applied for time capital T. The change in momentum for P is going to be mass, which is 10, times final velocity, which you're told is 4.75, minus initial velocity, look out for the double negative there, which produces a value of 65, so T is 65 over 13, which is 5 seconds. Marks for that one. There's a method mark for calculating the impulse correctly, an answer mark for coming up with the 65 here, and an answer mark for the correct 5-second answer in here. This is the second part of the same question, but it actually takes a different tack altogether and looks at a different topic involved in impulse and momentum, but I thought it was also an interesting little area to think about. Again, if you're working on this at home, please do pause at this point and work it through. The next slide, we're going to go through the whole of this 8-mark solution. Okay, so the ball's initially 3.125 metres above the ground. The ball basically is projected at this angle below the horizontal, so it's going to travel down, it's going to hit the ground at an angle, it'll bounce off, come back down, hit the ground again, and bounce back off once more. And so we're looking for the angle with the horizontal of the ball's trajectory immediately after the second bounce on the ground. So let's have a little think about how this is going to behave. First things first, we noted in the specification check at the start of this session that the horizontal, or the velocity of the particle parallel to the surface, is completely unchanged. So we can say here, in this case, the horizontal velocity, horizontal speed. So the horizontal component of speed is completely unchanged throughout. So that's going to be 14 cosine 30, and that's going to be equal to 7 root 3 meters per second. So we always have this velocity of 7 root 3 in the horizontal direction. Vertically, we've got several sections of motion to think about. So first of all, we've got the drop from the original point to where it first hits the ground. So I'm going to suggest that that could be somewhere around about here. And we need to know the velocity with which it hits the ground in order that we can, in the vertical direction, in order that we can work out the velocity it comes off at. It's then going to hit the ground again over here, and the velocity that it hits the ground with and the velocity at which it bounces back up again, those are going to be of interest to us. Okay, so vertically, and I'm just going to put here vertically to first strike. So this is, I'm interested in what happens between the point at which it's projected and the point at which it hits the ground for the first time down here. In the vertical direction, our initial speed downwards is going to be 14 sine 30, the component of that initial velocity, and that's going to be equal to 7. The acceleration in that downwards direction is equal to g, 9.8. The distance is our, oh, I'll just run out of space there. The distance is going to be our 3.125. And we're looking for the final velocity. So this is just a straight Suvat equation. The one that combines u, a, s and v is going to be v squared equals u squared plus 2as. Substituting in, v squared is 49 plus 2 times 9.8 times 3.125, and if we work that through we end up with our final velocity there as being 10.5. So the vertical component of the velocity as the ball hits the ground for the first time, just sketching that down here, so as it comes down and hits the ground for the first time, the vertical component of the velocity there is 10.5 meters per second. As it bounces back off again, I'm just going to sort of grade that movement down a little bit. Obviously these would be at a concurrent point where it hits the ground, but I'm just going to kind of slide it along a bit for clarity. So after it hits the ground there, we can use our Newton's experimental law and say that separation speed is E times approach speed. So it comes off the ground here at 0.6 times 10.5. So the speed with which it leaves the surface there is going to be 6.3. Further down the path, it's going to hit the ground again, and by symmetry, this bounce here, basically it's going to do something like this. The vertical speed as it hits the floor again there is going to be 6.3 again, just by the symmetry of that parabola. It'll hit the ground at 6.3 again, and it'll bounce back off at E times that, so 0.6 times 6.3, which is 3.78. Okay, so after it hits the second time, as it rises off the ground, it has an upward component of velocity of 3.78 meters per second. It's got a horizontal component of velocity, remember we wrote that down back here, of 7√3. So the angle that the velocity makes with the horizontal after that second impact, that's the angle that I'm going to put in here. So I'm going to say that tan theta is going to be 3.78 over 7√3. You can tap that into your calculator, and that gives us a value of theta of 17.3 degrees to 3 significant figures. So it's quite a shallow angle. Having started at 30 degrees, it's shallowed out quite a bit by the time it's taken that second bounce, because it's losing so much energy in each of the impacts. Let's just check out mark scheme for this. There is a mark for the horizontal component, so a B mark here for the horizontal component of the speed being unchanged throughout. There's a B mark for correctly calculating the initial vertical speed, and there's an answer mark for, a method mark for using the Suvat equation correctly, and an answer mark for coming up with the 10.5 value here. There are then M and B marks, method and B marks for the velocities after the first strike and the second strike. And finally there's a method mark for using the tangent of the angle here, and a final answer mark for 17.3 degrees here. And that brings us to the end of this session. I hope you found that useful. Please do take the time to visit the Further Maths Support Programme home website at www.furthermaths.org.uk. It's a fantastically useful site for both students and teachers. There are lots of further activities and events advertised on that site, and I'd strongly recommend taking a look at that. Thank you very much for your time.